So now, welcome on stage, dear Margaret. Margaret Kocherga is the CEO and founder of Margik, and today she will talk about advancing OLEDs with materials for diverse industry applications. I hope that is right.
Let's go ahead. So let's start a little bit with the rehashing of what is the benefit of organic light emitting diode or OLED. They consume less power, they're thinner, lighter, traditionally safer for your eyes and well-being, as well as the environment. They are brighter, as well as to the human eye, they are brighter, and they can have potential for multiple form factors such as bendability. But there is still challenges such as limited lifetime in comparison to some of the alternative technologies that are already on the market. Still, there's battle of low efficiencies for several of the colors of the OLEDs. The manufacturing still remains fairly expensive until Whitney gets us to the mass roll-to-roll production. And then we still utilize rare earth elements for a lot of these materials when we produce them or make them, or a lot of emitters especially use a lot of rare earth and heavy metals, which then poses challenges at the end of the lifetime of these devices and their recyclability. So the problem remains in the OLEDs that we need more efficient emitters. We must develop matching transport and ejection layers to make sure these emitters perform to the best of their capability. And then printable manufacturing requires also simplification of a stack. So a 12-layer stack is no longer really possible in the printability scheme of things, but in the evaporative technology, that is typically okay. An evaporative method is the most commonly used right now for display tech, but it is too expensive for lighting purposes. So what Margik approach is looking at mimicking really the performance of currently used materials, which are usually known as to be coordination complexes. And instead of heavy metal or rare earth element, we're replacing it with silicon at the center core. So we're still securing that coordination chemistry, but remaining simple stereochemistry. We can remain the low dipole moments. We can gain chemical stability and thermal stability with these, as well as we would have low reorganization energies. We did a case study of a couple of hexacoordinate silicon complexes, and here is a few variations that we have looked at, trying to replace different end groups on the ligands, but also changing the ligands themselves ever so slightly to just understand how the system operates and if there is future of it in the OLED industry. So we looked at also how we can model and predict the systems with respect to experimental data and computational data, and we learned that we can pretty well predict their homoluma levels and energies, and which reflects into fairly predictable UV-Vis spectra, as you can see here. If you compare the left-hand side simulated to the right-hand side experimental data, they are very comparable. That being said, we also looked at the ability of these materials work as emitters, as well as the transport materials. So we can have fluorescence or phosphorescence, which are two main mechanisms of your energy losses, if you must say. So upon excitation, we can have either fluorescence or phosphorescence or both, depending on how these intersystem conversions work. So your fluorescence, fundamentally, maximum energy efficiency would be 25%. Your phosphorescence can gain you that extra 75%, which is one of the most commonly things right now on the market for emitters is thermally activated delayed fluorescence, which enables you to gain that extra efficiencies from that triplet state back to the singlet state. And then there's also triplet fusion delayed fluorescence, which is a little bit less common on the market right now, but this is something you will see definitely in some of the other talks tomorrow. So we do definitely experience phosphorescence with a lot of these compounds. As you can see in the video to the left, we did shine the UV lamp to excite the material, and then we move it away, and then we do observe that delayed fluorescence. So that posed a question, well, can we have TEDF emitters with these? And not quite with these materials exactly, but with changing and tweaking some of those ligands, we can definitely get that delta E to be less than 100 millielectron volts and get it to that thermally activated light fluorescence for some of the future emissions applications. We also looked at how stable these materials, and we took ALQ3 as somewhat the golden standard that is readily available to look at the photo bleaching rates, and we observe that these materials are typically a lot